Recording is about to start. Okay, so welcome to everybody. This will be our fifth webinar, the fifth International Legume Society webinar, and I'm happy to welcome here all the people that's already online and all the people that will see and will watch our webinar on YouTube, on our channel. Today, I'm very happy to have here Dr. Nesli Sozer from Finland, from the VTT Technical Institute in Finland. And the topic on today would be alternative to meat protein and animal-based products using vegetable and legumes in particular. Dr. Sozer has more than 20-year expertise on food material and science. And this webinar touches a topic that has been only briefly touched already in a previous webinar. In fact, in the very first one with Christian Wig, where we talked in general about the perspective and the opportunities about research issues and legumes crops in Europe. And now it's time to go to delve a little deeper on this very specific topic. And that's it. Basically, I'm happy to leave the mic to Dr. Sozer. At the end, at the very end of the webinar, we'll also have a brief announcement about our conference, our upcoming conference. So stay tuned, and please, Dr. Sozer, here is to you.
Thanks, Nelson, and good afternoon. I guess everyone is from Europe, so I can say good afternoon to everyone. Now I will start sharing my screen, and Nelson, I count on you. You will confirm.
Sure, I will check you.
Then that you are seeing it.
Now I'm seeing a partial full screen. So I'm seeing the main slide, but also a thumbnail on the right. When we tested before the recording,
so because you have seen it properly last time. How about now?
Yeah, now it works. So now you're full screen.
Okay, and it still continues to be full screen.
Yes.
Okay, all right. With the recording, it has changed the settings. But I will be mainly looking at the big screen because this is now difficult for me to see. So sorry if I don't manage to have the eye contact. But yeah,
there's no problem. I will monitor the chat, as I said. So if any of the attendants want to write something in the chat, I will keep the questions. And at the end, there will be time for either written or live questions.
Okay, all right. So let's get started. Yeah, thanks, Nelson, for the invitation and the short introduction. So today's talk will be focusing on, indeed, the opportunities and challenges of legumes as component of innovative foods that will be alternative to animal counterparts, meaning dairy analogs or then the meat analogs. So when it comes to the global challenges, of course, one of the biggest global challenges that we have is that how are we going to feed the almost 10 billion population that in this planet Earth by 2050. And of course, when it comes to feeding the people, one important component is the protein. So protein is an essential nutrient for our body. And when we look at the current protein consumption, it is mainly based on animal proteins, which is not sustainable, especially for 1 kilogram of animal meat protein. we need 6 kilograms of plant-originated proteins for the protein conversion. So it is indeed very unsustainable protein source. So we need alternatives, and in order to also looking at from the perspective of planetary boundaries, this alternative diet should be more oriented towards a plant-based dietary shift. Indeed, in the recent Eat Lancet report, plant-based foods have been positioned to be a sustainable, and then also taking into account the planetary boundaries, have minimal environmental impact on our current food production system. But when we look at the plant-based ingredients and the foods made out of them, we have to optimize them for taste, we have to optimize them for nutrition, and we have to optimize them for cost. So as I mentioned, I will first briefly touch in the challenges that we have when using these plant-based ingredients, but then also briefly mention how do we turn these challenges into opportunities. So indeed, when it comes to making a protein shift, we have to think about basically the major protein components, so milk and meat substitutes, milk and meat analogs. But this is indeed a very challenging task due to the fact that plant proteins in general and then animal proteins, they have quite distinct structural and conformational differences, which also creates a big difference in terms of flavor, also nutritional quality, different aspects of sensory functionality. Also, when it comes to finding these meat and dairy alternatives, of course, consumers are also maybe the general consumer is not ready to take these products into the daily use. So we have to also find ways how do we make these products more attractive to the consumers. Also from the safety perspective, the safety of these products, not only from the perspective of microbiological safety, but also from the perspective of allergens and so on, has not been studied much. So there is a lot to be tackled from both sensory, nutritional, and safety perspective. Different levels of challenges. So when we compare animal proteins with plant proteins, unfortunately, there are lots of anti-nutritional factors that restricts the applicability of the plant raw materials. This also pretty much applies to legumes, which probably you are very much familiar, especially again with legumes. There is the issue with FODMAPs, which causes stomach discomfort. Then oftentimes these plant protein sources lack some of the essential amino acids. So it might be that, especially with the legumes, it's also well known that you have to use them preferably together with cereal proteins to have the more complete amino acid profile. Then there are the allergenicity issues, and then since the plant protein sources have pretty much different kinds of antinutrients, they also have restricted digestibility compared to animal proteins. From the flavor side, there are off flavors depending on the source of the plant protein. There can be beany off flavors, green flavors, and then bitterness and astringency, which needs to be tackled. From techno-functional perspective, protein solubility is pretty much, I would say, if I pick two functionalities, solubility is the number one, which I would say that is very important, because then it affects the foam formation and then also emulsification and also colloidal stability. That's very important. And then the second one that I would pick, that's more related to the meat alternatives. How do we form this more cross-linked and fibrillar structure? So those are, if I pick two functionalities, those are the things that I would pick as, really ranked up above. Then I have already mentioned the microbiological issues, so the risks and control methods are not so advanced with these alternative products. So the solutions can be quite diverse, from breeding to the food product design to the way that we are producing ingredients. So from the ingredient side, we can tackle some of these issues by adding some different mechanical treatments, different ways of milling, fractionation, homogenization. Then there are thermomechanical treatments, some chemical treatments can be performed, and also microbial or enzymatic treatments can be done, including also germination. Of course, we cannot solve all sorts of different problems, so in the end we need to also utilize, depending on the application, some of the food additives such as stabilizers, flavor enhancers, and thickening agents. If I go case by case and highlight which are the functionalities that are critical for certain applications. So for egg replacement, of course, egg replacement is very important when it comes to fine bakery products. Foaming is very important there. Then with plant-based drinks, colloidal stability is an important technofunctional property. For yogurts, puddings, and jelly type of products, gelation is of course which gives the nice mouthfeel to these kind of products, and with the meat analogs, it's indeed the fibrous structure formation. And I will now give brief introduction to what are the possibilities from the extraction point of view. So, of course, when it comes to protein isolates, meaning that those ingredients which has more than 80% of protein, so it is rather pure, they have increased functionality. But the process, the wet extraction process, is the typical process that is utilized to extract the protein isolates. It's energy and water intensive. We are in the middle of an energy crisis now. It's becoming more and more important, the energy and water efficient processes. And obviously, probably like me, you are also following this discussion around processing and ultra processing. And of course, the protein isolates require several steps of heavy processing, which also causes loss of some of the essential macro and micronutrients, which in the end affects the price. So the protein isolates have much higher prices that indeed affects also the price of these alternative foods substantially. So from the protein separation technologies, I will first touch base to dry fractionation technology, which is which actually is a very efficient separation process, and it is widely used also for legumes. It can be also applied to cereals. One critical thing with dry fractionation is that if you have more than 5% of lipids in the grain or legume, then this will not work. You have to remove the excess lipid. And typically, the advantage of dry fractionation compared to wet fractionation is you are able to keep the native properties of the protein, because there is no heating involved, there are no solvents integrated, there is no water, and then again removal of the water, so you are able to indeed maintain the native properties. So in order to keep that, when you're in a situation to remove the excess lipids, the ultimate choice that we have is the supercritical CO2 extraction. And as you might expect, this also has pros and cons. So it's not a cheap process. However, at the moment, there are also some more innovative and industrially available mechanical separation technologies that can also be utilized to remove this excess lipid. Of course, solvent extraction can be utilized, but then it is to the cost of the functionality of the protein might not be that optimal when you start integrating also solvent extraction. Then you need to have different milling steps where you basically separate the particles based on the differences in the particle size. So in order to be able to use the dry fractionation, you have to ideally have less than 5% lipids, and then different particle sizes of the components that you wish to separate. This kind of separation, as I said, works very well with legumes. Specifically, we have been trying it with faba beans and pea, and you can reach 60% protein concentration in these samples. So the fine particles are the protein. Proteins are generally have fine particles, and then the coarse particles are typically starch and different dietary fibers. Benefits is that if you have more than 5%, for instance, we have been using the same separation technology when it comes to oats, which has really high amount of fat. When you remove the fat, you improve also the stability, storage stability, which otherwise might cause shelf life issues. As it is dry process, it has relatively low production costs, and then also it's microbiologically safe. There are no harsh chemical treatments, so then the proteins remain in native form, and then you can get high value ingredients, side streams from this whole process. I gave the oat example. I know this is the Legume Society, but this is a very nice example to put things in a scale. So oat oil is very valuable. So it's used in cosmetics. And when we remove the oats, even if with the CO2 extraction, since it's a high value component, it gives really advantages when you use dry separation technologies. The downside is that by no means, whatever you do with dry fractionation, you would be able to get isolates. So the maximum protein content you would reach, again, depending on the material, is limited to 60%. Of course, this means that it's a concentrate. So together with the protein, something else is there. And again, depending on the source, this can be starch or dietary fiber. And then if you want to increase the protein content even a little bit more, like let's say 2-3%, then it costs a lot on the yield side. And as I said, it is not that straightforward that this would work with whatever material or cereal or grain. If you don't have a distinct particle size difference between the starch, fiber, or protein component, this will not work. As I mentioned, we have used this in faba bean, dry fractionation of faba bean. we have been working with a special Finnish variety called Kontu that had a relatively high protein content. It was 36% protein in the starting wholemeal flour, and then it had 42% starch and 7% dietary fiber. As you can see, and this is kind of a little bit, it was in our one of early publications in 2015. We were able to get the protein content at 52%, but within the years we have also improved our dry fractionation technology, and today I can comfortably say that we are able to reach protein contents with 60% very easily. And you can also find now commercial products in the market which has been made with this process. Another new technology that that we have introduced is this cascaded use of combining dry and wet fractionation technologies. The advantage that you get from here, first you concentrate the protein in the flour by using dry fractionation. And then you remove the dietary fiber and then the starch. So you don't need to first do a wet process where you need to remove the starch, but you can first use this dry process and then keep the native properties of the dietary fiber component and the starch component. And you continue the process with fat fractionation, and you can end up with a protein isolate. Although this might sound in the beginning, okay, you are adding another extra step and so on and so forth, let me show you what are the advantages from this cascaded process. I will go a little bit out of what I have put here in bullets, but I will highlight the water usage. The water usage per kilogram of protein is remarkably lower. With remarkably, it's 50% less water you use than regular wet fractionation. And then when it comes to energy use, per kilogram of protein, you use with this kind of cascaded protein process 2 kilojoules of energy, versus when you are using totally wet fractionation, it is 7 times more. So indeed, from the perspective of the energy efficiency and water efficiency, cascaded use combining dry and wet extraction is much more efficient. Other benefits I would highlight is that typically when you do fully wet extraction process, you get a very low value residue, which you can hardly find any use, not to mention that you cannot put it in any food formulations. And then the extra benefit that you get compared to the dry separation process is that in this cascaded process, since you are first having the dry and then the wet extraction, you are able to tailor the purity of the material and then even include some in situ functionalization steps during the separation process. Now I will give some examples of dairy alternatives and what could be the opportunities in the dairy alternative space with legume proteins. So when it comes to production of dairy alternatives, let it be a milk analog or let it be a yogurt analog. If you look at this and then compare it with the animal milk and then the animal protein-based yogurt, there are very many unit operations involved. So basically you need to start with a flour typically, or sometimes concentrate, and then you need to degrade the starch and fiber components. Then you need to have a heat treatment involved, and then of course homogenization is an important step when it comes to the milk analog. And then since it's a yogurt analog, you have to continue with fermentation and add starter cultures and so on and so forth. And here the viscosity is very important because it very much changes with heating. You cannot think about a dairy or a milk or a yogurt analog without going through a first heating step. Indeed, heating step in general is an essential part of whatever we do. So when we look at the dairy analogs, the viscosity is also pretty much contributing to the overall sensory experience. So here what you can see is how viscosity changes by heating when we change the protein content in the mix. So the top level is 10% suspension, and then the lower level is 15% suspension. And when we go from pea flour to isolate, obviously we are increasing the protein content. So, and then you can read the viscosity values under each of these samples. So you can, with the same pea protein, if it's in the form of a flour, you end up getting something more like a dough at same temperature and same time. With pea isolate, it's more like a milk. When we are trying to predict the performance of a protein, flour, or concentrate or isolate in a yogurt analog, instead of going directly to the fermentation, where you get also all sorts of different results from the different microorganisms and so on, we prefer to start elaborating based on acid-induced gel formation. So here we have been using glucanodelta-lactone to acidify the plant-based milk and then produce the yogurt analog. And as you see on the right side of the slide, there is substantial difference, and these are all concentrates. So it's pea, faba, and oat concentrate. In the way that the pea and faba responding is totally different than oats. Especially after heating and acidification, when you look at the oat protein, there is no gelation. Gel formation is very important in yogurt type of products, and you are not able to achieve it with oat protein. So not all plant proteins are the same. And this is basically due to the fact that when you look at on the left side, the solubility of pea and faba is much different than oat. So it has much higher solubility in native pH compared to oat, that also affects the gel formation properties. As I mentioned in the beginning of my talk, the presence of galacto-oligosaccharides is one of the issues when it comes to application of legumes into these innovative products, because it really causes intestinal discomfort. And for that, we have been using alpha-galactosidase enzyme. And the reason that we have also studied here pea protein concentrate is that typically when you do wet extraction process, when you have an isolate, you are able to remove the galacto-oligosaccharides during the processing step. So, but then because of cost reasons, because of functionality reasons, if you wish to utilize protein concentrates, pea or faba or lentil, then typically these have much higher galacto-oligosaccharides compared to the isolates. And here we have used a commercial galactosidase enzyme and then a VTT enzyme, which has quite similar activity, but then the side activities were a little bit different. And as you can see, both were quite efficient in removing the galacto-oligosaccharides. And what happens with the enzymatic treatments, they might oftentimes influence the rheological properties, and this was not something that we have obtained with the galactosidase enzyme, and that was indeed one of the good outcomes from this study. So it didn't affect the viscosity of the final product. Versus phytic acid is one of the most, again, important anti-nutritional factors also for legumes, and it's due to the fact that as humans we don't have the phytase enzyme, so we cannot degrade the phytic acid, and its presence limits the absorption of minerals in the intestine, and then it also hinders significantly digestibility of the protein. So it has to be removed. And here it's the same also with the phytic acid. If you have a wet extraction process and working with an isolate, you have much less phytic acid content compared to a concentrate. And here what we have done is that we have used phytase enzyme to degrade the phytic acid, and we have used both P concentrate and Faba concentrate. And as you can see from the table, the phytic acid content was substantially reduced after 1 hour treatment with phytase enzyme. But here we got different viscosity responses from these two different legume proteins. So with P, there was an increase in the viscosity. Sorry, decrease in the viscosity, and then with the Faba, there was an increase. And here we have two hypotheses. It might be the phytase-induced release of calcium, or it might be something to do with the effect of this treatment on protein solubility and thermostability. But this needs to be further studied. And indeed, in one of our previous papers, we have also looked at the in vitro protein digestibility after treatment with phytase enzyme. And as you can see, there was a substantial increase in the solubility of the proteins, which means that they were better digestible after the removal of phytic acid. One way of, I don't have that data here, but I would like to also pinpoint at this point during this seminar is that, of course, enzymatic treatment is not the only way to degrade the phytic acid. So fermentation also degrades the phytic acid. But then one challenge there is that not necessarily all fermentation microorganisms or then the conditions that you use are able to degrade phytic acid as efficient as the phytase enzyme. The next example I will give is the meat alternatives and what are the opportunities when it comes to use of legume proteins in the context of meat alternatives. Typically, the meat analogs are produced by using high moisture extrusion technology. Compared to the traditional dry extrusion technology, it is a rather new process where you can get structures that really resembles the unprocessed meat, so really the wet meat itself. So it includes a twin screw extruder, which has a long cooling die, and the long cooling die is a very important step of this whole process, where and then the starting material should have preferably more than 60–70% protein in it. So with the action of the shearing and high temperature, the proteins start to denaturate, they melt, and then they start to align themselves in the direction of flow, and then they start to cross-link to form the fibrous structure resembling the meat texture. So here, again, if you work with isolates, typically they are fine, okay, but then you are missing micronutrients and you are also missing the cost element there. So it's oftentimes increases the production cost. So in order to make the protein concentrates work, one approach you can use is the cross-linking enzymes. And soon I will show you how combined use of transglutaminase, which is one of the most well-known cross-linking enzymes, together with protein glutaminase can be indeed utilized as an approach to create a stronger protein network, but also an improved functionality. So here you would see that we have worked with Faba and yellow pea protein concentrate. And this time, the third protein component was hemp. It was hemp protein concentrate. So we have followed the same processing steps. So we started with 10% suspension. We have first added a preheating step to open up the structure and then performed enzymatic treatment with combining trans and protein glutaminase as a cocktail. And then we have freeze-dried, and then we have performed high moisture extrusion. As you can see from the image, the upper part is without any treatment, so that's the native. And then the middle part shows the preheated control, and then the lower part picture shows the effect of cross-linking on these three different plant protein concentrates. So as you see, with the legume proteins, Faba and pea, it has dramatically improved the fibrous structure. However, with hemp protein, it actually caused an impaired fibrous structure compared to the native. And actually, the main reason for that is that, of course, when we are doing this extrusion processing, one experimental protocol that we use is to check the SS cross-linking by putting it to STS page. And then when we look at also the amino acid profile of hemp, it has low lysine content. And the presence of lysine is very important when it comes to transglutaminase, because it's a cross-linking that happens between lysine and glutamine component. Another way of designing this innovative product concepts is to take advantage of fermentation. And this particular slide also summarizes one of the recent projects that has received national funding, and we just finalized the project. And there we have combined both extrusion and fermentation. And how we have done that is that we first extruded pea protein isolate, and we have combined it with fermented pea protein concentrate. Here in fermentation, we used two different strains, so Lactobacillus lactis and Lactobacillus plantarum. We have stuffed them into vegan casings, and then we cook them to make this cooked sausages. And then we have performed trained sensory panel. And with the fermentation, we were able to remove the pea-like odors and improve the texture. So they were more chewy texture, and then we were able to bring in more this yeast-like odor which was appreciated due to the fact that indeed when it comes to meat alternatives, umami taste is one critical factor. So the fermentation was bringing this yeast-like odor and taste that was making these vegetarian sausages much more appealing. I will end my presentation by giving little bit maybe more different approach. So the hybrid foods are indeed, especially with due to the fact that we are going through this energy crisis, it's getting more and more important to utilize this hybrid approach. And with hybrids, what I mean is that combining plant proteins with the actual animal proteins that's produced by the animals. So combining plant and meat, animal meat, or combining plant protein with milk proteins. And a good example here can be that I don't know how much you are familiar, but then now we are seeing more and more these hybrid approaches. In Finland, for example, we have this pulled fish concept where there's also a new startup in that domain that has combined this low value fish, this small fish, with pea protein, and then turned it into, after extrusion, totally new application that really resembles the pulled fish texture. Also, plant-based ingredients can be combined with cellular agriculture ingredients or precision fermentation ingredients. And then here another good example is the famous Impossible Burger. Impossible Burger is based on pea protein, but then the bleeding factor is coming from heme protein, which, by the way, actually can be also found in legumes. But then they are obtaining this heme as a precision fermentation ingredient and have been combining it as a low inclusion, high performance ingredient, which gives the unique bleeding experience to this Impossible Burger. So here I will give an example from a recently ended EIT food-funded project where we looked at plant and meat hybrids. Here we have created hybrid extrudates from pea protein and combining minced beef. So it was 50-50 combination, which had different, the beef component had different amount of fat content in it. And if you can pay attention to the pictures after extrusion, you would see that we were able to get this time very distinct, fine, fibrous structure, which by no means you would be able to achieve if you are only processing the pea protein isolate or then using the texturized pea protein concentrate. So we got totally different new structures. But what was even more interesting was the sensory evaluation results performed by the trained sensory panel. When it comes to the pea protein concentrate, one important issue is and also with the pea isolate, is the pea flavor. That's not something that you would wish to have in a meat alternative product. But integrating a little bit of the meat component, we were able to get the umami taste to this pea protein concentrate, versus it didn't work in the pea isolate. So in that sense, here use of concentrate was a better approach and a more cost-effective approach. And with our previous knowledge, we know that fat content, the presence of animal fat, is very important when it comes to the release of this umami flavor component, taste component. And here, what was also good to notice is that the fat content, because if you remember, we had this lean, so 7% beef, and then the 17% beef, which had higher fat content. it had no effect on the intensity of umami. Saying that, and with that knowledge, the next step that we moved forward in our research at VTT was that, okay, we have now integrated meat lipids, but then is it possible to produce these meat lipids in a more efficient and sustainable way? And we have been utilizing, instead of animal cells, I know cultured fat cells are also utilized for this approach. We have been using microbes as cell factories to produce these lipids much efficiently. And this, the contribution of lipids into the flavor and texture is not only limited to meat. In dairy, it's also very important from the flavor and texture wise. And these plant protein and cell egg hybrids can be also utilized to overcome the flavor and texture challenge in meat or dairy analogs. When it comes to animal fats, it's basically the triacylglycerols. That's the major component that we are targeting. And then there are certain yeasts that is called as oleogenous yeast that can produce these tags in a very efficient way, meaning that 50% of the total dry cell mass can be triacylglycerols. The lipid yield and then the composition profile can be also tailored by controlling the growth parameters. Just as an example, we have been recently utilizing different yeast and filamentous fungi, and this strain D, which you see in the screen, that was able to produce stearic and palmitic acids, which are very essential. Again, by background literature, we know stearic, palmitic are very essential when it comes to getting the meaty flavor, but then also myristic acid, which is the more saturated, so C14, was able to also express in this strain D that's important from the melting properties perspective. So the next level in these alternatives is indeed to, in order to close the gap between the animal counterparts and then the plant-based, let it be a legume protein or let it be a cereal protein, is indeed now more and more focusing on the fat domain, because when it comes to these alternative proteins and making this dietary shift, the primary attention has been on the protein domain, but it's not only us, but also other researchers and industry is also now noticing that the fats and the presence of fats with the right nutritional profile is very important in closing the sensory gap between the plant-based products and then the animal counterparts. So some key takeaways from this lecture is that indeed plant proteins can be utilized to make a dietary shift. Here legumes are very important, especially legume concentrates. They can deliver both the protein and dietary fiber. In the beginning of my talk, I have highlighted that proteins are very important in our diet, but when we look at Europe, we don't have actually a protein intake problem. We have a fiber intake problem, dietary fiber intake problem. And that means that instead of looking into more these isolates and so on, we should be more looking at how can we utilize the concentrate so that we can get more of the dietary fiber, but also the protein domain. And in order to enable this shift where we need to consume more plant-based foods, okay, we can consume legumes as legumes, but you cannot really increase the intake substantially. You need processing and you need a diverse group of plant-based foods. And indeed here processing, as I have showed some examples already, can be utilized to make the plant-based foods more healthy, reducing the nutritional components, improving the digestibility, more appealing, because even if you can create the most healthiest product in the world, by the end of the day, if it's not appealing, nobody will consume it, so you will not deliver the health benefits. Then these hybrid foods combining plant and animal proteins or plant and precision fermentation ingredients have a huge potential in closing the gap between the plant and animal products. So this was my last slide, and thanks for your attention. And I would be happy to take some questions.
Thanks, Nesli. And that was a really nice presentation, full of a very interesting point. I will start with one question that came through the chat, and that basically raises two topics which have only been briefly touched in your presentation. One is the one big source already of protein is soybean, and I will widen the discourse if you have something on the topic on both soy, which is very used, but not central in Europe for a number of reasons, and on lupin, which is a rising crop with very interesting features. If you have thoughts on the topic. And the other topic that was asked in chat was about breeding. So what could be the role of breeding? Most of your presentation was technological in nature, but what would be a good shift of breeding? Usually focuses on total yield as a main feature, as a main trait for improvement. So what kind of shift would be required in breeding for embracing this kind of products?
Yeah, of course there are certain things that you can handle also in the breeding side, but I must admit that that's not something that we focus at VTT, and
Sure.
and as my presentation tells, I'm more expert in the field of ingredient and food production, so my role starts. But I know, for instance, when we started, it was roughly around this protein discussions were started to be hot like 10 years ago or so on. We started working with faba beans. This vicine and convicine was very much in the interest of the research. And then we have been also discussing with different breeding companies and so on, and they were like, don't worry about vicine and convicine. After 10 years, that won't be a problem. We are working on zero vicine and convicine varieties. And I don't know if it has now entered into the European market. I think France is already producing this vicine and convicine varieties, but I don't know how much it is in the mainstream. So still, with this breeding, of course, it can work in the long term, but I think in the short run, to enable this dietary shift, we need to maybe a little bit more focus on the after breeding side. But as I said, this is not really my expert area.
Okay. And on the topic of using soybean or other legumes, why did you end up using faba beans and pea? And why was it considered to use a different species?
There was a good reason about faba beans. It's one of those rare crops that can grow in Finnish climate. It's an ancient crop for Finland, so that was the reason. And then the pea was more like a benchmarking for faba.
Okay. I have a second question from the chat. Victoria, can nutritional yeast help to reduce the off flavor in meat analogs?
Well, nutritional yeast can be utilized, but not to reduce, to mask. You cannot reduce the off flavor just by simply adding the nutritional yeast. And I know there are some approaches, especially companies are utilizing the nutritional yeast, but then you must keep in mind that it's adding additional ingredient in the list. And then, of course, there is now more and more interest to have more clean label. So instead of using nutritional yeast, my approach would be to add their fermentation. So you create in situ the umami. Or it depends very much. I'm reading the question. Could you define the source of flavor? It depends on the raw material and what kind of processes it went through. So there are different chemical components that's associated with different kind of flavors. There is not a single off flavor.
Okay. Do we have any other questions? It appears that we are satisfied. So I again thank Nesli for her beautiful and very interesting presentation. We are now going to close this webinar, but just don't leave, and because the International Legume Society is getting closer and closer to our 4th conference that will happen next September in Granada. In these very days, we'll have all the details out about venue and deadlines and all this kind of thing. Probably the deadline will be something around at the end of May or mid-June for your contribution. It will be a great opportunity. We skipped 1 year because of COVID. We skipped a couple of years because of COVID, and we are now more than happy to have this venue in Spain. The venue is wonderful. It's Granada is a beautiful city, and it would be a good chance to see each other live. So once again, I thank Dr. Sozer, and thank everybody that attended. The presentation will be online in a few hours, hopefully. Okay, thanks to everybody, and that was it.
Thank you. Have a nice rest of the day. Bye-bye.
Thank